Okay, so for lab, this is recitation for lab 4, and for lab this Tuesday, what we're going to be doing is we're going to be performing a titration. Okay, now last semester, or Chem 105 lab, we performed a titration as well, and in that titration we put into our solution or into our container, we put some sodium carbonate, right? About 5 grams of sodium carbonate, some water as well. We had a stir bar, and we used a burette to titrate the sample. Okay, and in the burette we had HCl. And we also had one more thing in there. I don't know if you remember what it was, but we had to put an indicator. And the indicator changed color when the reaction had come to the pH that we wanted it to. And that's what the indicator was for, so we could know that the reaction had reached completion. Okay? So for this lab activity, you're going to be utilizing the microlab and monitoring the pH with a pH probe versus the volume of titrant, or the stuff that you add, right? This is called the titrant that you add to the titration. And your curve will look something like this, right? If you monitor the pH versus the volume, initially at least, the volume of, and we're going to be adding a base, so NaOH, that you add to the solution. Now, in this titration reaction, the reaction that we're monitoring is the titration of H3PO4, or phosphoric acid, 1 proton at a time. First, it's going to go to H2PO4 minus, and then H2PO4 minus is going to take another proton and eventually go to HPO4 2 minus. Now, if you continue to go from HPO4 2 minus to PO4 3 minus, you can. However, we're just going to monitor the first 2 steps in this process. The reason we're only going to monitor these first 2 steps is because the third one is difficult to detect simply by monitoring pH as the volume of NaOH is added. All right. We talked about a pH curve last time we did a titration a little bit. I'm not sure if you remember exactly how it was going to work. So in this titration, we start with a low pH because we're adding acid into our burette. All right. So into our sample, and we're not actually using an Erlenmeyer flask. I guess we're using a beaker. So we're going to have an acid, which is the H3PO4, right? And it tells us over here in the first step, fill the, well, let's see, where's it at? Pipette exactly 5 milliliters of the 0.1 molar H3PO4 solution into 4 250 milliliter beakers. And then we add an amount of water. And again, just like last time, the amount of water doesn't really matter because the pH won't change until the phosphoric acid is consumed. Okay? So, we have our beaker, and we add a little bit of phosphoric acid, and then we're going to titrate it with, and that's what it says here, the dropping burette is going to be our burette that we're going to use. We're going to titrate it with 0.1 molar sodium hydroxide. 0.1 molar sodium hydroxide. Now, there's a video, and I'll get to that video here. There's a video on the Canvas page that shows how to set up this titration. So let me show you that video. So here's the Chem 106 Lab Canvas page. If you go to Lab Videos here, and then you go to the Lab 4 video, this video here will show you how to set up the apparatus. Okay? So, again, we're going to be using the
All right. So this
we're going to be using the, you can see as we go through here, we're going to be using the microlab, and this shows how to set it up. So I expect you to watch this, 11 minutes 37 seconds, not too long. All right, to learn how to set up the titration setup. Okay, so as we monitor pH versus the volume that we add, we're adding, again, base. So we're going to be adding, I'm just going to put the base, which is sodium hydroxide here. We're going to be titrating in the sodium hydroxide. And as that sodium hydroxide accumulates and becomes more of it, then the pH will increase and become more basic, right? Increasing pH means that the solution is becoming more basic. All right? But just like the previous time, because we're only adding little bits of base at a time, and we can look at this equation again, little bits of base at a time, so the H3PO4 is giving up its proton and becoming H2PO4 minus, right? H3PO4 is losing a proton to the base. Here we have it written as it losing it to the water, but it's really losing it to the base, but it doesn't matter. It's still just losing a proton and becoming H2PO4 minus. Okay? All right. And so because you're only adding base gradually, then the pH won't change right away because all the base that you add is initially taken up by the H3PO4. After all the H3PO4 is consumed and you just have H2PO4 minus, the pH necessary, which is called the pKa, to make H2PO4 give up its proton, right, to become HPO42 minus, the pH necessary is higher. Therefore, you get an increase in pH, an increase in the hydroxide ion concentration, until H2PO4 begins to take up protons, to give up protons. All right? The result is the addition of sodium hydroxide doesn't change the pH much until all the H3PO4 is consumed, and then there's an increase in the pH as the more hydroxide ion is added. Then, as soon as the pH gets high enough that the H2PO4 will begin to give up proton, then you get another plateau like this. And then you're going to get another increase as HPO42 minus. The pH has to increase, and then at that point, HPO42 minus will begin to give up its protons. So this is the shape that we're going to get when we titrate the phosphoric acid. All right? So let's look at this a little bit closer. There's something interesting about pH curves in general that is very helpful. So we're adding base, and as we add base, the pH changes. Well, let's just look at this first, what we call equivalence point, or end point. Sorry, let's look at this first end point. This point here is when all of the H3PO4, right, has been converted to H2PO4, and there's no more H3PO4 to take or to give up protons, and therefore the pH begins to shift more drastically. At this point in the titration, the concentration, or the acid, is mostly in the H3PO4 form. When we get to this point, all of the H3PO4 is consumed, and we just have H2. All right? And then, looks like I lost my camera. Then, as we add more base, the H2PO4 will continue to be consumed until we get to our second equivalence point, or second end point, which means that all the H2PO4 is gone, and now we just have HPO4 with a 2- charge. So what's interesting about this is the amount of sodium hydroxide that is required to reach the end point, the number of moles of sodium hydroxide that you had to add to get this far, will equal the number of moles of the H3PO4 that we had in the sample. Now in this case, we know how much H3PO4 we did. The lab we did in Chem 105, we didn't know how much sodium carbonate was in the unknown, but this was a way to identify it. So titration can be a way to identify the concentration of an acid or a base or whatever it is that you're monitoring the reaction of. However, in this case, the titration isn't for monitoring the concentration of the H3PO4. The titration, the thing that we're interested in here, in this case, is trying to identify what the K is for this step and what the K is for this second step. Okay, what the equilibrium constant is. And we have so if you're halfway in between the beginning, where you start with mostly H3PO4, and the first endpoint, where you have no H3PO4 left, almost all H2PO4 minus. If you're exactly halfway in between that beginning and that endpoint, then the amount of H3PO4 that you have, half of it is consumed and been converted to this. The amount of H3PO4 that you have now is H3PO4 at this point is half of it is dissociated. So you have half of your initial concentration. So we could say 100% of this is H3PO4 at the beginning. This would be a way of thinking of it as 0%, 0% H3PO4 now, right? It's really 100% H2PO4 at this point, 0% H3PO4, right? So, at this point, which is halfway, then your half of your stuff is H3PO4, and the other half is the dissociated amount. And we gave that a special name. When you're at a pH, right, that half of your material is dissociated, that then is what we call the pKa of that reaction. If it's an acidic reaction, pKa. If it's just any reaction, you call it pK. But they call it pKa for this acidic reaction. Therefore, so you can monitor how much base was required to go halfway, and then find out what that pH was at halfway, and then that pH, whatever the pH is there, will equal the pKa. And then, just like for pH, you can convert from pKa to Ka, because 10 to the minus pKa will equal the Ka. So this is another way to identify the equilibrium constant for a chemical reaction. For example, the first halfway point to the first end point, that will be the Ka for this reaction. And then the distance between here and here, halfway in between there, whatever the pH is there, that will be the pKa for the second one. And you can use this relationship again, 10 to the minus pKa, to to find out what the Ka is for the second step. This second reaction is the H2PO4 converting to the HPO4 2 minus. H2PO4 minus going to the HPO4 2 minus, which is this second reaction here. And that's what we're after. We want to know the Ka for this first and the Ka for this second deprotonation or reaction. Okay? So you're going to set up your titrations, perform them all, and then find those. Now, once you have a titration curve, like this one, then you're going to plot the data in Excel. And after you have the data plotted in Excel, you're going to take the first derivative of the graph to identify the endpoints precisely. All right, so if we have the data from a titration curve, all right, now this is just the data from a single titration curve. I can take this data and I can plot it, insert a scatter plot, but we'll just choose a smooth line like that. So this is the titration right to the endpoint. So we start, and then we get our titration right to the endpoint. Well, in this reaction, or in this titration here, we want to know exactly where the halfway point is between this beginning point and the end point right here. And for this one here, it's kind of obvious because it's nice, it's a perfect titration curve, but your titration curves might be a little more difficult to determine exactly where the halfway point is. So what we do is we take this plot. Let me give a quick adjustment here. I want to make sure you guys recognize that this is the pH. And this is the volume of base, which in this case was, well, units will be milliliters. And you're going to convert that to moles at some point, but, well, yeah, I'll just put in moles of base right now so that you don't get confused, or get less confused. Moles of base, all right. Actually, I guess what we should do is we should do concentration of base, and the units are moles. Okay. So, this titration curve here, we can find out exactly where the endpoint is by taking the derivative of it. And to take the derivative of the titration curve, we make a new line here, a new column, that we plot the change in x over the change in y, or change in y over change in x, rise over red, right? So I'm going to do that by taking the change in y, the y is the pH value, so this minus this, that's my change in y. I have to put those into parentheses, and then I'll divide that by this minus this, and put that in parentheses as well. Okay, and then I'll double click there, and that'll fill that down. I'll copy this and paste it right here. And now this one, I'm going to click here, and I'm going to drag the, instead of being on the pH, I'm going to have it be on the first derivative curve. Okay, so it looks like these first 2 points are a little out of whack, so we'll delete those. But after that, I can see the points that are the sharpest by looking at the peaks in this curve here. Now it's kind of hard to see because, again, whoops. I'm going to delete some of this data here. your titration curve will look something, or your derivative will look a little more like this. This might be a little bumpier or whatever, but there will be one point here that will indicate the volume at which the slope is the highest. You can copy the derivative curve and put it over the titration curve like this. You can also right-click on this and say Format Data Series and say put it on a secondary axis. That helps us see exactly where the endpoint is, and then you can hover over that point there and see that our x-axis is 99.85. That's our endpoint. So half of that, which would be a little less than 50, would be where our equivalence point is. Equivalence means that the amount of the H3PO4 is equivalent to the amount of the H2PO4. The concentrations are the same. So if I go to 50 here, and I can see what the pKa is by finding out what the pH was at that halfway point. All right. So you're going to perform this titration about 3 times, and then, let's see, anything else that we want to remember? Carry out 3 or 4 titrations as indicated in the directions, and then between titrations you should rinse the pH probe, and then from that data you're going to determine the pKa1 and pKa2 of phosphoric acid. All right. And that should be it. So again, the goal of this lab is to identify the the Ka and the Ka2 of this, and the pKa and the pKa2 of these chemical reactions here. All right, make sure you watch the lab video that shows you how to prepare the setup. Okay, we'll see you on Tuesday then.